In today's class, we will try to learn about grouping of the capacitors. Capacitors can be grouped or connected or combined in either of these three ways. Capacitors in series, capacitors in parallel, and capacitors may be combined with series and in parallel. We call it that last one as mixed combination of capacitors. Okay, and we will try to learn about also the energy stored in a charged capacitor, rather the potential energy of a charged capacitor. We will learn that one also, and then we will also try to prove that the energy stored or potential energy stored in the series combination and in parallel combination are equal. And we will also learn that loss of energy on sharing of charges by the two capacitors. Okay, let's try to learn all these three things in this class today. So let's take up that these capacitors, let's take it that C1, C2, C3 up to so on be connected in series. Okay, as shown in the diagram here, connected between the two terminals A, B, and it is connected again through a source of EMF or battery, of whose potential difference is denoted by V through a key K, and the terminal B or the point B is connected to earth. That means B is earthed. As it is connected in series, what happened, these capacitors are connected in series. The peculiar property of the series connection in the case of capacitor is that same charge will be stored in each of these different capacitors, even though their capacitance are different. So that is the peculiar property. So same charge will be stored in different capacitors having different capacitance. Okay, but the potential difference across these two plates of each of these capacitor will be all different. That means let's take it that V1, V2, V3 so on up to Vn be the potential difference across these different capacitors C1, C2, C3 up to Cn respectively, right? Obviously that the sum of this potential difference V1, V2, V3, if you take it that sum V1 plus V2 plus V3 so on up to Vn, then it will be equal to the applied potential difference, right? So let's see the description. Now in this description, see, let this system of capacitor is connected to a source of potential difference or a source of EMF or potential V, and it is denoted by this cell in my diagram here with B. And as I said, let V1, V2, V3 are the potential difference across these capacitors. These are all written here. You can pause this video and you can copy it, okay, if you want to make notes. Now this potential difference, I told you that the potential difference here, that means from the battery, that will be the potential difference between the points A and B. So the potential difference between A and B will be equal to what? The sum of the potentials across the different individual capacitors. So your B will be equal to V1 plus V2 plus V3 so on up to Vn. Mind you that the peculiar property in the series connection is what? The charge on each and every of this capacitor stored will be same. That means Q remains constant in the case of series combination, right? Yes. And now in the next slide we will see this just as a repetition. Okay, V1 plus V2 in that next slide I just repeated it so as to make a continuity. Okay, now if you want to find out that that potential, this V, if you want to write that potential, this potential is what the total potential. So your total potential will be equal to what? Q by C, where Q is the charge that is flowing in that circuit. Okay, and C is nothing but C is the equivalent capacitance. What is meant by equivalent capacitance? Equivalent capacitance is nothing but this is the total or net or resultant capacitance of all those capacitors connected in series. For our case, in some book or in some reference book, you may find this C as denoted by CS. CS so as to represent what? Your series combination. Okay, S for series. So likewise you may find this as CS like this. It may be denoted by CS like this, C suffix S, S for series. Got it? So what happened, we are just representing by C only, and you have to think in your mind that this is nothing but this C is the equivalent capacitance connected in series for those capacitors C1, C2, C3 up to so on Cn. Now this B1, the potential difference across that first capacitor, that will be also equal to Q by C1, where C1 is nothing but the capacitance of the capacitor. Okay, the capacitor itself is also denoted by C1, and its capacitance is also again denoted by C1 again. Okay, so don't make confused. And this is what the potential difference for the second capacitor. B2 will be equal to what? Q by C2. So on like that. If you keep on writing for that of the nth capacitor, it will be what? Q by Cn. I mean your Bn will be equal to Q by Cn. Okay, where nothing but this C is nothing but the resultant or the equivalent capacitance of the combination of the capacitors. Okay, so the whole term are having in the numerator as what? Q on both sides of the equation, right? So you can cancel it, and so the resulting equation will be what? 1 by C will be equal to 1 by C1 plus 1 by C2 and so on up to plus 1 by Cn. Thus what, in parallel in series combination of the capacitors, the reciprocal of what? Your equivalent capacitance. Okay, the equivalent capacitance 1 by C, we call it that as reciprocal. So reciprocal of the equivalent capacitance is equal to the sum of the reciprocals of the individual capacitance. Got it? So this is the resulting formula for the resultant what? Capacitance of the capacitor connected in series. Now you must be remembering about that series combination in the case of what? Resistors, and parallel combination in the resistor that you have done in your class 10, right? So that this formula, if this C is replaced by Rp, then it will be equal to 1 by R1 plus 1 by R2, like that. So this seems to be the formula for the equivalent resistance in the case of resistors, right? So just the opposite. If it is for the formula for parallel combination of resistors, then that will be equivalent to what? The series combination in capacitors. So you have to think in that way. Okay, you have to use some mnemonics. Okay, the formula for series combination of capacitor will be equivalent or similar to that of formula of parallel combination of resistors. Okay, you have to think in that way. Now let's go quickly about the capacitors connected in parallel. So in the case of parallel combination, the peculiar property for parallel combination is that there in each of these capacitors, okay, the amount of charge stored will be different, because if Q amount of charge is sent out from this source of EMF or battery or cell, then what happen? This, as the capacitors are having different capacitance, it will have to store different charges. So naturally different value of charges will be coming out from the source of EMF, and it will be passing through these capacitors, right? But the peculiar property is that even though the charges stored are different depending upon their capacitance, as they are connected in parallel across these 2 points A and B, the potential difference across these capacitors C1, C2, C3 up to Cn, they will have the same potential difference. Got it? So same potential across different capacitors having different capacitance. That is the peculiar property for what? For parallel combination. Whether it may be for resistor or series, doesn't matter. So in the case of parallel combination of these components, so let's take it for today as capacitor. So same potential difference across these C1, C2, C3 up to what? Cn will be having the same potential, and that potential will be equal to the potential difference across AB, across these 2 points. These 2 points means what? It will be having the same potential difference across this source of EMF. That means B again. Got it? Now let's take it in that way. So your charge, the total charge that is coming out from the source of EMF, okay, that will be equal to the sum of this q1, q2, q3, so on up to qn. That means these are the charges that are stored in each of these different capacitors. Okay, so this q, the total charge is coming here, and from this charge it has been distributed to each of these branches across these different capacitors, right? So your q must be equal to what? The sum of these different charges that has been distributed from the same charge q. So your q will be equal to what? q1 plus q2 plus q3 up to so on up to qn, right? So now let's try to express it again in terms of that known quantity. Now if we know that this potential difference across this is V, and if we can replace this all of these capacitors by a single capacitor having its capacitance C, then that C will be known as equivalent capacitance of all these capacitors. Okay, so equivalent or resultant capacitance is nothing but if a capacitor of having capacitance C, if it can replace two or more capacitors, then we call it that capacitor as equivalent capacitor, and its capacitance is known as equivalent capacitance. Okay, so your Q is equal to BC. Suppose all these nth capacitors, n capacitors I should say, if it is replaced by a single capacitor, then that single capacitor is known as what? Equivalent capacitance of all these capacitors. So what happened if we replace this by a single capacitor, then instead of this n capacitors you will have only one single capacitor of whose capacitance is denoted by C here, and the potential difference across it will be what? B. Charge stored in it will be what? Q. So your Q will be equal to what? BC, right? So that is what I'm doing here. Got it? So likewise, as we did in the case of series, this C may be replaced by CP, C suffix P, okay, so as to represent equivalent capacitance for parallel. So likewise, if you try to write for these different charges Q1, Q2, Q3, so on, then you can write it as BC1, BC2 like that. Okay, so in all the terms, okay, on both sides V are all same, so you cancel it those V and you will get it that equivalent capacitance C will be equal to what? C1 plus C2 plus C3 plus so on up to Cn. Now let's take the analogy that we have learned in the case of resistors. So this is for parallel combination of capacitors. So parallel, you have to take the formula for that opposite one in the case of what? Series resistor. Okay, series connection of resistors. So what happened in the series resistor? What happened? Rs is equal to R1 plus R2, so on like that, na? Individual sum of the resistors. Likewise here also parallel CP equivalent capacitors connected in parallel will be equal to what? Sum of the individual capacitance of those capacitors connected in parallel, right? So C will be equal to C1 plus C2 plus C3, so on up to Cn. Got it? And let's see now the potential energy stored, okay, in these charged capacitors. What will be its formula, right? What is this potential energy? Potential energy is nothing but this is the amount of work done, okay, that work done in transferring the charge to that capacitor. Okay, that amount of work done is nothing but that will be stored in the form of its potential energy inside that parallel plate capacitor. So potential energy of a capacitor may be defined as the amount of work done, okay, to charge the capacitor. Suppose if you have done the work of, say, suppose 1 joule in transferring some definite amount of charge to a capacitor, then that amount of 1 joule done in charging that capacitor will be stored in the form of electric potential energy inside that parallel plate capacitor. Got it? That is nothing but we call it that as potential energy of a charged capacitor, or simply what energy is stored in that charged capacitor. And mind you that the potential energy stored will be in the form of electrostatic field energy. Got it? In the form of electric field energy, you can say. So let the plate of the capacitor be charged to dq. Let's try to find out that small amount of charge dq, okay, is transferred from the source of EMF of having, say, constant volt say V. Okay, then what happened? Small amount of work done by the battery or by the source of EMF or from any source, let that work done be denoted by dW. Small amount of charge dq transferred to that capacitor. Okay, let's take it that it has been transferred from a constant potential say V from the source of EMF or from any other source. Then what happened? The small amount of work done will be denoted by dW, and that dW will be equal to what? V into dq. This is coming from your definition of potential difference. Potential may be defined as potential V may be defined as the amount of work done in bringing a unit positive charge, right? So work done per unit charge, we call it as what? Potential. So dW by dq will be what? Potential V. So your dW will be equal to what? V into dq. So V can be replaced by what? Q by C. From that expression of capacitance C is equal to QV, you will get it that your V will be equal to what? Q by C times dq, where Q is nothing but the charge of the capacitor at that instant. That means this Q is nothing but this is an instantaneous charge, okay, at that moment, at that instant means at that time. Got it? Now let's see the total work done, okay, required in delivering or charging to say suppose charge Q, capital Q, to the capacitor is what? We have to integrate this small such dq so as to reach the charge stored up to what? Capital Q. Got it? So let's try to charge that capacitor from 0 charge to capital Q charge. Okay, so we need to integrate such small work done from where to where? From charge 0 to charge capital Q. Got it? From charge Q, from charge that from charge 0 to charge Q. So that will be the expression. Okay, so if you want to do this integration, then what happen? Your C, capacitance of that capacitor, that will be what? A constant quantity, as long as you have not changed the the dimension. Okay, the distance between the plate, the common area, that will remain same, constant. Okay, so your C, capacitance C, will be treated as constant, and so you take it outside the integration and you will get it as what? Q integration of Q dq will be what? Q square, okay, divided by 2. You must be remembering how it is coming. Let me show you. Okay, now if you have that integration of x to the power n like this dx, then what is the formula? The formula is what? X to the power n plus 1 divided by n plus 1, right? N plus 1, right? This is the formula actually. Now, so in our case, what happened? Instead of x, we are having q, and instead of this power n, we are having as q to the power 1. So what happened? If you do the integration, then what happened? You will get q 1 plus 1 means q square, 1 plus 1 means 2. So you will have q square divided by 2. Got it? Q square divided by 2 here. So what happened? That q square divided by 2, it is here. So the integrating limits are from where to where? The lower limit is 0, upper limit is what? Capital Q. So if you replace this variable by the upper limit first, then it will be capital Q square divided by 2 minus 0 square divided by 2. So if you take the multiplication, the second term will be 0, as Q will be replaced. This variable will be replaced by the lower limit. So 0 square by 2 is 0. So we will have only half Q square by C. Now this is the resulting formula, and we can replace this resulting formula q square by c by what the those formula that can be connected with that c is equal to bq, like that. Okay, so your q will be equal to what? C q will be equal to what? C by v, right? So if you do that formula, then the resulting equation will be equal to what? Half cv square, okay, is equal to what? Half qv. No, you have a relation that in the case of capacitance, C will be related as what? C will be related as what? QV, right? So that your Q will be equal to C by V. Am I right? Right? So if you replace it, that formula from here, this QS, C is equal to QV, so your Q will be equal to C by V. So if you do that formula here, instead of Q, if you replace by what? This Q replaced by what? Your BC, then what happen? It will be C square V square. So 1C will be cancelled and you will get CV square. Likewise, if you replace it this B or C by Q by V, then what happened? B1B and this B will be cancelled, and what happened? You will get as half QV. So the potential energy stored in a parallel plate in a capacitor, okay, or a parallel plate capacitor, you can say, that will be equal to what? Half Q square by C, or half CV square, or half QV. This, just to remember, I will tell you one mnemonic that we know that in kinetic energy, in the case of mechanics, it will be half mv square mass. Okay, when a body of mass m is moving with velocity v, then we take it that kinetic energy as half mv square, like that. Now, so in the case of capacitor, you just take it as half what? cv square, like that. If you remember this, then you can give for a different formula by using that formula, that q is equal to bc, right? In that way you can also do it, that one. Next, let's try to prove that the energy stored in the case of series and in the case of parallel combination, the total energy remains same. That is what you can take it this in the form of question. Okay, to prove that energy stored in series and parallel combination of capacitors are equal, and each will be equal to the sum of the energies of the individual capacitors. Not only that they are equal, the total energy will be equal to what? The sum of the individual energy or potential energy stored in each capacitors. Okay, so in series and in parallel, you can divide this in two columns, and I will tell you in a brief way. Okay, we know that equivalent capacitance in the case of series, 1 by Cs will be equal to what? 1 by C1 plus 1 by C2 plus so on up to 1 by Cn. Let's do it for series first. Okay, so your work done, okay, or the potential energy, you can say, in the case of series, that will be denoted either by W or US. This will be equal to half Q square by C. Just now we have done that potential energy, half Q square by C. This will be equal to half Q square will be same. Okay, so instead of this C, the equivalent capacitance CS, okay, that will be replaced by what? 1 by C1, 1 by C2, so on up to 1 by Cn. So if you do that opening of this bracket, then what happen? You will have the potential energy stored for this first capacitor, second capacitor, so on up to that nth capacitor. So these are nothing but these are W1 potential energy stored or work done in doing what? Charging of Q amount of charge to that capacitor C1. This is the work done in storing or charging that capacitor C2 with the amount of charge Q, so on, like that. So we see that the work done or potential energy stored in series combination will be equal to what? Sum of the work done or sum of the potential energy stored in these individual capacitors C1, C2, C3 up to so on Cn. Got it? So let's see in the case of parallel. We know that in the case of parallel combination, equivalent capacitance is denoted by what? Sum of the individual capacitance. So Cp will be equal to C1 plus C2, C3, so on. Okay, and your potential energy, we have found that in that previous slide that your Cp will be equal to half Cv square, right? Potential energy, total potential energy. So your total work done will be equal to what? Half V square. Instead of this equivalent capacitance, you just write it that C1 plus C2 plus C3 up to so on. And if you open the bracket, then this will be the potential energy stored in the individual capacitor. Okay, first capacitor, second capacitor, so on up to what nth capacitors. Okay, so that means these are nothing but this potential energy. Okay, the total potential energy stored in the parallel combination will also be equal to the sum of the potential stored in each of the capacitors. So these two are all equal, right? This in the case of series also, total potential energy is what? Potential energy, sum of the potential energy of the individual capacitors in the case of series as well as in the case of parallel. And now let's see for the loss of energy on sharing of charges by two capacitors. Okay, now let's take it that these C1 and C2 are the two capacitors, okay, having potentials V1 and V2 respectively. Now before connection, after charging it, this capacitor and capacitor C1 and C2 having capacitance C1 and C2 with potentials V1 and V2 respectively. Okay, so before connection, the total energy will be what? U1 plus U2. U1 is the capacitance for this, potential energy for the first capacitor, and U2 is the potential energy for the second capacitor C2. So total potential energy before connection will be what? U1 plus U2, sum of the individual energy. So it will be equal to half C1 V1 square plus half C2 V2 square, right? So taking half common, the total energy before connection will be equal to this expression, right? Half C1 V1 square plus half C2 V2 square. That is what we have seen in this, right? So this is the total potential energy before connection. And let's see for after connection. Now the total charge that will have after connection, what happened? Q1 and Q2. Now Q1 is what? Actually Q1 is nothing but V1 C1 will be Q1. So what happened after connection? There will be surely a transferring of charge from one capacitor to another capacitors having what? Difference in potentials. Okay, it will flow from higher potential to lower potential, right? So what happens? Some charge will surely be transferred from one capacitor to another capacitors, but the total charge will remain same. So before connection, what happened? Q1 will be the charge stored in the first capacitor and Q2 in the second capacitors. So what happened when Q1 and Q2, even though there is a sharing of charge or transferring of charge takes place, the total charge will remain same. So let the total charge be denoted by what? Q, and it is equal to Q1 plus Q2, right? So your Q, let's try to express this Q1 and Q2. We don't know this Q1 and Q2, but we know that its potential V1, V2, and its capacitance C1, C2. So we know those things. So let's try to express this charge in terms of those known quantities. So Q1 will be equal to what? C1, V1. Q2 will be equal to what? C2, V2. So let's express it in that way. So after combination or connection, its equivalent capacitance will be what? C1 plus C2, because it is connected in what? Parallel, right? They are connected end to end, right? So what happened? The equivalent capacitance will be what? C1 plus C2, right? So we have found that this equivalent capacitance, and then what? Total charge. So we can easily find out the total energy, okay, after connection. Try to remember the total energy before connection was what? Denoted by U, and it is denoted equal to what? Half times of C1 V1 square plus C2 V2 square, right? You just remember, because in the next slide I will not show you this one again. Okay, so in the next slide, what is there? Total energy stored, okay, in the case of parallel combination, let's denote it by U prime. Before connection it was denoted by U only, and let's try to denote this after connection, the total energy that is there inside the capacitor. okay, after connection, that is denoted by U prime. So it will be equal to half Q square by C, right? So we know this total charge, we know this total capacitance or equivalent capacitance. So let's replace it. This total charge will be what? C1 V1 plus C2 V2. Okay, and its capacitance will be equal to what? Equivalent capacitance will be being connected in parallel, so it will be C1 plus C2, right? So if you try to take the difference, the energy before connection U and the energy after connection, then if we will have U minus U prime, and U means what? Before connection, that is this one, after connection, that is this one. Okay, so if you open the bracket, then what happen? You will get like this, half C1 V1 square plus C2 V2 square. Okay, like this. This is the actual, okay, the expression. If you open the bracket in the form of a plus b whole square, then it will be a square plus b square plus twice ab, right? In that way. Now if you take the LCM, then for these two expression, then it will be what? 2 times of c1 c2, that will be the what? LCM. And if you do that simplification, then you will get like this, c1 b1 square, okay, c1 square b1 square plus c1 c2 b square. That means if you take this as a LCM, then you need to multiply. 2 is there, no doubt. So what happened? C1 will need to multiply here, no? Then you will get it c1 square b1 square. C1 need to multiply here. That means c1 c2 b2 square, like that. Similarly, the c2 will need to multiply here and here again, in that way. Okay, if you do that simplification, then the like terms with opposite sign will be cancelled each other. Okay, the c1 c2 c1 square b1 square will be cancelled with this minus c1 square b1 square. Same is the case with for c2 square b2 square will be also here 1 minus c2 square b2 square. So after cancelling these like and opposite terms, okay, then what happened? You will get this c1 c2 b2 square, c1 c2 b1 square. Okay, and what happened? The last one is minus twice of c1 c2 b1 b2. Okay, these three terms, let's take it this as a first term, this as a second term, and this as a third term. Okay, so that all the terms are having c1 c2 a factor c1 c2, right? So you take it that common, and you take it that b1 first, then b2 square second, then minus twice b1 b2. So within this bracket, it is of the form of what? A1 square plus b square minus twice ab. So it is of the form of a minus b whole square, right? So b1 minus b2 square. Got it? Then what happened? This is a square term, and your capacitance will never be a negative quantity. And from this resulting equation, we come to the conclusion that this last expression or last this term after simplification, it will be always a positive quantity. It will be always a positive quantity. So if it is a positive quantity, the subtraction of any two quantity gives you a positive quantity, means what? This u is greater than u prime. Okay, if this u prime is greater than u, then it would have been coming out to be minus. So what happened? This shows that the difference of this energy u minus u prime comes out to be positive, means what? U is greater than u prime. That means energy, total energy before connection, that means before sharing of charge, what happened? That total energy is greater than total energy after sharing of charge. So that means while sharing, some charge has been lost. I mean, some energy has been lost, not charge. Okay, charge cannot be lost. Okay, charge cannot be decreased. Charge will remain constant. I have to say that some energy has been lost. Where this energy has been gone, then if it is going to loss, then whether it will violate the conservation of energy, the question comes up, right? So what happened? The energy doesn't loss, but that loss in energy, it has been used in transferring or in moving the charge through the connecting wires. Okay, the connecting wire has its own resistance, and to overcome those resistance in the transferring of charge, that much amount of energy has been used up, okay, in transferring those charge from one capacitor to the another capacitor. Okay, so that means what we said, that as if it is positive, U is greater than U prime, and so we can say that without any what hesitation, we can say that there is always a loss of energy. Okay, there is always loss of energy on sharing of what charges between the two charge capacitors. Okay, got it. So with that note, we will try to end this today's class. Okay, thank you.